Okay, before we continue on this subject, the next section is actually about the complex. But before we go to that sections, I would like to review and perhaps adding some additional parts on the sections, which is the uh, upper and lower bounds. So let's get started. So let me start with uh, that we have this theorem that uh, we would have upper or lower bounds, okay, if we define the polynomial functions with some terms using the syntactic divisions. Okay, so basically what this theorem says that when we deal with the first one, the first part, if we divide px by x minus b and b is a positive number, uh, and we define with the syntactic division, and if the row that contains the quotient and remainder has, which means the row that is in the results in the results sections, they have no negative entry, then B is an upper bound for real zeros of P. And if we divide with another terms, which is x minus a, with a is the negative number, then the last row or the results row, um, they are alternating non-positive and non-negative, then A will be lower bound. Okay, so I think we could just take some example. So if we have p of x, x to the power of 4 minus 3x squared plus 2x minus 5. Okay. Let's say that this px, okay, the px is lie between -3 and 2. And we would like to know whether this -3 is upper or lower bounds, meaning uh, the limit set for the polynomials. Is it -3 is on the top or on below, or 2 is on the top or below, upper or lower? Okay, so we could say we are going to use the syntactic division. So let's divide p of x divided by x plus 3 or p of x divided by x minus 2. So we start with the first one. Or let's say we start from the x minus 2. Okay, we start from here. Well, I think we can start from anywhere. So let's start from this 2, and then we have 1, 0, -3, 2, -5. And we have 1, we have 4, and we have 1, we have 2, we have 4, we have 8, and we have 3. Now we see that these entries all non-negative. Okay, and let's try the second one here, and we can compare at the end. 0, 1, 0. So this is -3. This is 9. This is 6. This is -18. And this will be 48. And this results in 43. And we could see that it's positive, negative, positive, negative, positive. So this is the entry here in the last row, or the final row, is alternating in sign. Okay, so based on what we have, -3 is the lower bound, okay, because it has, and 2 is an upper bound, okay, because we see that this is no negative entry, and this is alternately non-positive, non-negative. So we say that this will be lower bound, and this will be upper bound. Well, basically, upper bound and lower bound is we are just checking some numbers whether they are upper or lower. Okay, and you will see uh, the um, the differences on this last row. If you find the last row all non-negative, then it will be upper bound. If it is alternating in signs, then it will be lower bound. Okay, so I think it's quite understandable. Okay, that's the first part on our course. Next, we are going to set some examples, how to use the Descartes of rule, and then finding the real zeros, and so on and so forth. Okay. All right. Now we are going to use some set of examples using the Descartes rule, and of course, with additional information about upper bounds and lower bounds, how this could be or this could help when we are looking for the real zeros from polynomials. Okay. Okay, now we are going to set up some example. So let's say we have a polynomial and we have 2x with power 5 plus 5x with power 4, negative 8x cubed, negative 14x squared plus 6x plus 9. Okay, so we could start with taking the possible rational zeros, or possible zeros if you would like. We could set the factor from this 9 and factor of this 2. So possible rational zero, we could set factor of 9 over factor of 2. Okay, let me help you to guiding you step by step. So 9, it has factor 1 plus minus, and then plus minus 3, and then plus minus. Is there any other factor? I think just 9. I think just these 3 numbers. And for 2 is plus minus 1 and plus minus 2, right? So we are having this rational forms of factor of 9 over factor of 2. So we could have plus minus half, plus minus 1, plus minus 3 over 2, plus minus 3, and plus minus 9 over 2. I've arranged this from the lowest part until the higher number. Okay, so this is the rational zeros. Okay, we check some numbers. Well, let's try some positive number first. Okay, well, if you would like to check if you would like to check the how many positive number, we could check using the Descartes rule. Let's say we check the Descartes rule, so we know how many positive number we will have. So we are going to check. So there's 1, and then there's 2. So 1, 2, so 2 positive. So this it's going to have 2 positive zeros or 0 positive zeros. Okay, so it could be 2 or 0. Okay, and then we could check also the negative zeros if you would like to know. This will be negative 2 x5. This will be plus. This will be minus. This will be minus and plus 9. So 1 and 2 and 3. 1, 2, 3. So 3 positive or negative, sorry, negative zeros, or 1 negative zeros. Okay. So the Descartes rule for the variation of signs, if we have, for example, this one here, we have 1, 2, 2 variation of signs. Every time we need to minus by the even number 2. So we could have 2 positive zeros or 0 positive zeros. And when we have 3 like this negative zeros, so the possibility will be 3 negative zeros or 1 negative zeros. How we could get this 0 and 1? This is from 2 minus 2 and 3 minus 2. So it's become 0 and 1. Okay. So this will be for Let me write here. This is for positive zeros, and this will be for negative zeros. So for positive zero, it could have two positive zero or nothing. Okay, for the positive zero. So we could check the positive numbers. So let's check using the syntactic divisions. Let's check the um, using 2, 5, negative 8, negative 14, 6, 9. Let's divide with 1 over 2. So this will start with 2. We have 1. We have 3. And we have negative 5 over 2. It's getting not really good number. So we could say that perhaps we are going to see uh, non-zero situations at the remainder. So good check also. This will be 72 minus 9 is 63 over 8. So okay, it's not okay now. Not zero, right? So we could skip this 1 over 2. So let's keep going and stay optimist. So 2, 5, negative 8, negative 14, 6, and 9. Oh, let me copy this so we could have this for other calculation as well. Okay, this will be 2, 2, 7, 7, negative 1, negative 1, negative 15, and this will be negative 15. And interestingly, this is negative 9, and we have our 0. Yes, yay, we got our 0. So this is, we could say that P at x equal 1, our functions will be 0, right? And then we have the other form here. So we could write our px, and every time you get 0, do not use the same or the original equation to find another zeros. Rather, using the one that you have been reduced to. So for example, for our case, let's use this one, okay? Use this. So we could write our p of x as x minus 1, and then write this is constant x, x squared, x cubed, x4. So we have x4. So 2x4 plus 7x cubed minus x squared minus 15x minus 9. Okay, and then the next part, to find another positive zeros, we are going to use these sections to get through our syntactic division. So let's use this. Okay. So we have two positive zeros or 0. So we already have 1. So perhaps the statement that's saying 0, it's wrong. So we should have two positive zeros. Okay, that we are going to check and confirm. Now we check the 2, 7, negative 1, negative 15, negative 9. Okay, and also we have the same set for the rational zeros. So we have 9 and 2. So we could have the same possible rational zeros, which is the same with this equations. So we have half, 1, but half we could remove that. So we could check let's check 1 again if we want to try, just to checking whether it's still okay. Oh wait, it's 8, this is 8, right? and it's not 0. So let's keep moving. The next part after we have 1 is 3 over 2. So let's try 3 over 2. Yeah, why wouldn't I copy this part? Okay, well, I think that's okay. 3, then 15, right? So this will be 14. This will be 21. This will be 6. And this will be 9, and it's 0. So we get another 0. And it's true that we have two positive zeros now. So we will have that when p at x equal 3 over 2, this will equal to 0. And again, we now have our p of x. We could write x minus 1, x minus 3 over 2. Then we can write the whole thing here, 2x cubed plus 10x squared plus 14x plus 6. Well, uh, we could try to write down and multiply all by 2 um, for our case here. Or rather, we could factorize 2 outside. So we will have x cubed plus 5x squared plus 7x plus 3, right? And then the 2 will be multiplied to here. So 2x minus 3, right? So we get it right also like that. To make it more clean and seems okay um, to further investigate. Okay. Okay, let me copy and move to the next page. You could pause my video and if you want to write some notes. Okay. Okay, let's go. Copy here. Okay, this is our px. And we could see that we will have, we could also check this. Okay. If we, using the Descartes rule for this one, no variation of sign. So of course, no positive zeros, right? As we already mentioned that the big one, we already have this two, right? Two positive zeros. So the next thing we could check is the negative one, right? And from the possibility of the Descartes rule from here, the the possible zeros are factor of 3 and factor 1, right? So we only have plus minus 1, plus minus 3, and because we are not having any positive 0, we could try negative 1 and negative 3. So let's do that. So we could have 1, 5, 7, 3. Let's say we try negative 1. So 1, 4, 3, and we are now getting our zeros. So this is zeros. So we are going to have our p of x. The big equations that we are going to have is x plus 1 and then x squared plus 4x plus 3. Okay. And of course, this one we could factorize, right? We could factorize x plus 1, x plus 3. So x plus 1 we can take squared. So p of x minus 1 to x minus 3, x plus 1 squared, and x plus 3. Okay. And by the structure, we could also conclude that the zeros is 1, 3 over 2, -1, and -3. Okay. So let me go through some review. Okay. So the Descartes rule and our possible zeros, we could repeat this process many times. Depends on how long our equation is or how high our degree. Okay. For example, okay, our example here is having fifth degree of polynomial, which means we start by taking some guess from these possible rational zeros. We take our time at the beginning to try and test. Okay? So testing this all this set of numbers. Okay. Okay. And now to narrow our search or our conclusion to narrow, we could check how many positive zeros that we are going to find and how many negative zeros. Okay. And we get that from the positive zeros, we could have two positive zeros or nothing. And from the negative zero, we could have three or one negative zero. Okay. Okay. Now we start one by one, take our time. So we start from the positive zeros. We take half and then one. And then for x equal 1, we get that it's going to be our 0. Okay, and then we are going to write a new structure or new form from our original equation. We could write x minus 1 and then 2x to the power 4 and so on and so forth. Okay. Now from these sections, we are going to evaluate this with syntactic division and finding another zeros. Okay. So this could help our solving problem, because if we are using these numbers, we are going to waste our time too much, right? So we should narrow our searching and use this as our syntactic division process. Okay. So we using this, and then again we take our time to see our possible zeros. Okay, our possible zeros, and we could see that we are going to have the same or similar numbers. Okay, and we could start from 1. Okay, we could start from 1, and we could also start from 3 over 2. Okay? Because 1 is not 0, so we start with 3 over 2, and it's 0. And also, see this last row, I forgot to mention. The last row is said that it's all positive, which means this is an upper bound. Which means we do not need to check any further positive zeros because all the remaining candidates is greater than 3 over 2. So we don't need to check the we don't need to check 3, we don't need to check 9 over 2. And of course, to confirm that we are not going to have another number, is we have this two positive zeros that will be it is best for our or it's the best advice for us, right? This is two positive zeros. Okay, and then we continue and write the structure. Okay, the structure, and we are going to evaluate this x cubed plus 5x squared plus 7x plus 3. Okay, so we evaluate. Okay, we evaluate, and we already have this as two positive zeros, right? So we could continue. Okay, we could continue. solving the syntactic deficiency. Okay, and we get that it's not having any positive zero because of the Descartes rule. Okay, so the only way to have is just checking the negative one, right? And negative one, we check, and okay, it's zero. But this is a little bit weird if you just see the result. Okay, the result is it's have two positive zeros, right, and two negative. What is our Descartes rule at the beginning? We have two and we have three, and this two and three is perfectly aligned with the conclusion that this is a fifth degree. But remember that we have actually three because we have this two. So it's actually -1, -1, -3. Okay. But the number itself, it's just 4. Okay, because the -1 is having multiplicity. Okay, I hope you still remember. It has multiplicity. And it will also affect the Descartes rule. Okay, it will also affect the Descartes rule. Okay. So that's how we find that our zeros is these four numbers. Okay. So I hope this can help in general, helping to guide you to find the zeros. And also the syntactic divisions, whenever you have a polynomial with high number of degree, you could always use the syntactic division to help you factorize this polynomial function. If you are still in calculus 1 with me, later in some sections, in chapter 4, we are going to learn that we are going to apply our calculus to sketch a curve. Okay? And sometimes the curve will have some higher number of polynomial degree. And the way we are going to confirm, one method is using this syntactic division. And to help you guide through the Descartes rule, the upper bound, lower bound, and also how to find the possible zeros, it's also helping. Okay? It's not really like becoming the requirement, no, but it's more like supplement. It will help you in the process of learning. Okay, but in our basic of math, you need to master this process. Okay, you need to master this process. Okay, at least to get through this syntactic division. I hope. Okay, let me write here. I hope you master the syntactic division. Okay. Okay. The next sections, we're going through some more examples. I hope I can give you enough examples, sufficient example, so that you can understand more. Okay. Okay. Now we are going to have some examples. Okay. So let me give you another examples. Okay. So let P equal, let's say the x to the power 4 okay, let's say we have that. Okay, now we could try from the possible ratio, so factor of 12 divided by factor of 1. So this is P over Q, if you remember. So this will be plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. Okay. Now we could have, using the Descartes rule, let me write this all together. Okay. So there is no alternating signs here, no variation of signs. So P has no positive, or right, with positive zeros. So we could think on the negative. Okay, we check. And we have 1, 2, 3, and then 4. So we have 4. What should we write for the 4 variations? So 4 negative zeros, or 2 negative zeros. And since 2 is still, we can write also 0. Negative zeros. Okay, so when you have more than 2, like this one, like for example, maybe you have 3, you could write 1. Okay, and then, okay, it's just 2. If you have more than 3, like 4 or 5, you could have 3, you could have 1. Okay, so I hope you understand on how we write this possibility. Okay, now we're going to take this into our consideration. So perhaps we are going to have 4 negative zeros, 2 negative 0, or 0 negative 0. So let's try to check only negative number. So check negative 1. Okay, I think not okay. So let's go the other number. Okay, still not okay. Oh. So let's try negative 3. Okay, not okay also. We need to check another one. Let me check. Also not okay. So perhaps we need to check negative 6. Well, perhaps there's no zeros for negative zeros. So perhaps all the zeros will be, so all zeros are a complex number. It's possible. Okay, let me go through another example that I think we need to start from something that can be imagined. Okay, I think we could try. Okay, let's change the equation, the questions. Okay, let's change the other questions, I think. Okay, so as we have P equal this. Okay, we could try from finding the possible ratios, the factor of 9 and factor 1, right? So we have 1, 3, and 9. I think we already did this. Let me check. I forgot. Have we done this before? I think I haven't. Okay, we can try. Okay. Okay. Let's check the Descartes rule. So 1, 2, 3. So 3 positive or 1 positive. Zeros. Okay, 4 zeros. And then okay. Only 1. So 1 positive or negative, sorry. 1 negative zeros. Okay. So we could check. First is the positive one. So we could check through the syntactic division. So let's say we have 1. Okay, I think it's not 0, so let's change again. So let's change to 3. It's negative 12, it's 2, 6, and this will be 3, and 9, and 0. Okay, so we have zeros. So we have, we can write as usual. We rewrite this form, and we have the cube. Okay, now we are focusing on this part. Okay, we can see that this has 1, 2. So 2 positive zeros. And if you want to check the negative 1, it has 1 negative zeros. So we could check the negative 1, and we can check that it has a factor of 3 and 1, right? So I think we could check the negative 1. So 1, negative 4, 2, and 3. This is negative 5, 5, right? So 7, negative 7. I think it's not there yet. So we could take the, I think we could check the negative 3. I think not. Let's check the other part. I think we could check 1. I think maybe I wrote some mistake before. Okay, sorry if I wrote that. I think we could check another 3. Another 3. Okay. Oh, I think we get another 3. So it's multiplicity. So we could write that this x minus 3, and then squared is x squared minus x minus 1. And we could have finding this through our quadratic formula if you would like. So we could check the x1, 2 is equal minus 1, so plus 1, or maybe let me write 1 plus minus 1 minus 4 minus 1 divided by 2, right? So it should be 1 plus minus square root of 5. So we could have this. Okay, so we have zeros are 3 and 1 plus, and the other part, sorry. Okay, I hope you're still getting familiar with the Descartes rule, finding the possible zeros, okay, and then using the syntactic divisions, right? Okay, so the next sections will be continuing this chapter, okay? Okay, the next sections is about the complex zeros and fundamental theorem of algebra. Okay, now let me get through the okay. That one, and then again another one. Okay, let me get through this theorem. Okay, so first is fundamental theorem of algebra. So every polynomial that has degree equal or greater than 1, if they have complex coefficients, they will have at least one complex zero. Okay. So real number also, let me write here the explanations. So real number also is also a complex number, right? So the theorem applies to polynomials with real coefficients as well. So this theorem shows that the polynomial can be factored completely into linear factors. Okay. So if we take this p of x as a polynomial of degree n equal or greater than 1, then there will be exist complex numbers with a it's not 0, such that we can factors this out like this. Okay. Okay, let's say if p at least has 1, 0, let's say it's c1. Okay, let's write p of x is x minus c1, and then we have another function of x, q. Okay, and then the q degree, okay, is degree of n minus 1. Okay, and if we apply the theorem, then this could be factorized into another c2, and then it's resulting another function of x, and now I'm writing a q2, and this q2 is degree, now before it's n minus 1, now it's n minus 2. Okay, and c2 is also a 0 of the q1x. Okay, so c2 is 0 of q1x. Okay, and I think from what we have before, we already did this, and this is how we usually write down the results of the polynomials after we did the syntactic divisions, right? Okay, and we can also write, and if we repeat this process, we could have until Cn, until n times, okay, until n times, n degree polynomial, okay. Okay, let me give you an example to see practically how this would work, okay. So let Px is equal, okay, let's say we need to find the zeros and we need to factorize completely. So I think we could factorize. If we have this, one way to do it is we could factor x squared, and then we have x minus 3, right? And then plus x minus 3. And then from this x minus 3, we can factor out also, and we could write that as well. So x minus 3 is x squared plus 1, okay? We know that this is one of the zeros, so zeros is 3, but this one is we called irreducible factors, okay? We could see that when we take this equaling to 0, this will be equaling to this, and of course this will be a definition for imaginary number plus minus. Okay. So zeros are, or when x equal 3 and x equal imaginary, positive imaginary and negative imaginary. Okay, so we could write the factorization completely as x minus 3, x minus I, and x plus I. Okay, like that. Okay. Okay. And similarly, we see another example. Okay, you can pause the video if you want to take notes for this example. Okay. Okay, now if we take the p of x as x cubed minus 2x plus 4, okay, if you would like to find the zeros, okay, remember that we might use the factor that will be, it's factor of 4, right? Factor 4 and factor 1. So we could focus on factor 4, so plus minus 1, plus minus 2, and plus minus 4. And we could also check using the card rule. So we could check 1, 2, so 2 positive zeros. And also we could check the negative 1 if you want. So it has one negative zeros. So we could check the positive one first. So we could check 1. Don't forget that it has squared, but it's 0, so we do write 0 for the x squared terms. Then negative 2 and then 4. Okay, we start from 1. I think we could try almost every number since it's not too much, not too many. I don't think this is working. So let's check another one. So let's check 2. Okay, I think we could check. We check using the negative 2. Let's say negative 2. Okay, it's zeros. So this one is true, right? And we could write down that the p of x is equal x plus 2, x squared minus 2x plus 2. Okay. And of course, if you see the definitions, this definitions is it's irreducible factor, so we could write through the quadratic formula, or let me just refresh your memory to take the complete square. So let's say we have this supposed to be equal to 0. Okay? So we are going to have x squared minus 2x, and let me put minus 2 on the right side like that, and we are going to plus something. So I think we need to plus with 4, right? Oh no, 1, sorry, plus 1, and then this should be also plus 1. So we could have x minus 1 squared, and then this will be minus 1. So we will have square root both sides, and we are going to have an imaginary numbers, right? So an imaginary number, so we have x minus 1 equal plus minus imaginary number. So x is 1 plus minus imaginary number. So zeros are, you could write this, x plus 2, and then x, oh no, not x, sorry, 1 plus x minus, yeah, well, let me just write it with the zeros. This will be confusing for you. So I just write zeros is when x equal -2 and x equal 1 plus imaginary number and x equal with 1 minus imaginary number. Okay. Or if you would like to write the structure, let me just write it again. I think we can write like this and plus. I think this should be correct. Okay. Okay, now let's go back a little bit, showing the example that we have done here, just to show you that since we have here in this process, in the Descartes rule, we might have this, right? 3 positive or 1 positive and then 1 negative. Okay? And our results, we have 3, and then we have the positive and then negative, right? So we have 2 positive and 1 negative. It seems that it's not worked here. We have 2 positive, but we have here actually 3 positive. There is no 2 positive. So how does it become 3? Remember that we have this is multiplicity. So it also counts into our Descartes rule possibility. So although the number is 3, but the factors, it comes out twice. So we should write the zeros are 3, but this 3 is multiplicity. So this should be accounted for this Descartes rule 3 positive. Okay, so we have 3 and then another 3. So we have 2 positive and then 3 positive. This. So this 3 positive zeros, and this will be the negative zero. And it's true. See, it's fit with this predictions. So the Descartes rule can predict what kind of zeros we would have. And this is our next sections, which is the multiplicity. So zeros and multiplicities. So every polynomial of degree n equal or greater 1, it has exactly n zeros, and provided that a zero of multiplicity k is counted k times. So we need to count this multiplicity as the how many zeros it would have. Okay, So if we need um, to factor out, let's say, or finding zeros from this, okay, and since we can factorize this uh, slowly, so let's say we factor out 3x from here. So we have x4 plus 8x squared plus 16. And we can also factor out this part. Okay, we can factor out. If you confused on how to factor out this, we can let the x4 becomes let's say b squared. Okay, and we can write b squared in another paper. So b squared plus b, right? So 8b plus 16, and we could write this, and this will be plus 4, or this is b plus 4 squared, and b is uh, x squared, right? X squared. So we could write this: p of x is equal to 3x, x squared plus 4, and then squared. And of course, we say that the zeros is 0, so x is 0, and we could take this and equaling this to 0, and we have plus minus 2 imaginary number. Okay. Well, we could also check through the Descartes rule if you would like. So we have no positive 0. And we could also take the p negative. But I think we could check with this. Okay, interesting. This is and no negative 0. Interesting. I think we could confirm through the Descartes rule. Well, nonetheless, we could write down the formulations. So we factor out this imaginary. So we could write this 3x, and then this will be x minus 2i, and x plus 2i, and then square. So we could see that this is multiplicity is 1, right? And 2i, so we can say 0 is having multiplicity 1, 2i multiplicity is 2, and negative 2i multiplicity is 2. How we do know multiplicity is from this square here, okay? So the factors or the polynomials is degree 5. So whenever we find the polynomial degree 5, um, n equal 5, so these zeros expected to be 5. I mean 5 zeros, 5 zeros. But we have 1, 2, 3. But actually, because it has multiplicity 2, this is also 2, so this is 2, 2, and 1, so it's become 5. So that's how we count 5 zeros from multiplicity if we have multiplicity, okay? All right. Yeah, I think that's the this sections. Okay, this is all about the um, complex, okay, and imaginary numbers. All right, now we are going to continue our explanations. So the next sections, I will finish off this part here, and next sections will be continuing still the same chapter, chapter 3. So we have rational functions. And perhaps we could also add a explanation about the asymptotes. Okay, I hope you still remember what asymptotes means. Its concept also mentioned a lot in calculus, and I think I will just give you some brief explanation on rational functions, some tips, and the details. I think it's better to focus more in calculus. So if you have taken calculus, so we just have some review on rational function and asymptotes for now. Okay. So rational functions, let's say we have Rx, is based on a form of the denominator, the numerator and denominator, let's say of a function. So like P and Q, like this one. Okay, and we know that the P and Q, they are both polynomials. Perhaps to start with, for um, for a simple explanation, we could see a functions. For example, the 1 over x. I think it's easy to follow and to imagine. And to understand how this 1 over x works, we could take some time to check some x's value and check what's the results on the function itself. So let me just give you the result. Sorry. Okay. So let's say we have x. Okay. If we have x negative 10, it goes by negative 0.1. If x is increasing in the negative numbers, then the result is negative 0.000001, and the same thing happened when we put x equal 10 and we increase the numbers until, like for example, 100,000 or maybe 1 million. The result will be approaching zero. So when x goes to negative infinity, the f of x is going to be zero. When x goes to infinity, the f of x goes to also zero. So it does say something here that when we try to build up our graphs, and we take just a small numbers to imagine where it does how it does works, and how the coordinate will appear in the graphs. So we took some x from negative 2 to 2, maybe take sometimes for 1 half also, and we could see that it's going to be reciprocal. So this is what we are going to get. Okay, and remember that when we have this, okay, when we have the x going to infinite or negative infinity, meaning x is going to be goes there, right, or goes here, there is some invisible line that is appearing. We call this invisible line an asymptote. Okay, the same thing happened also for the vertical line. So when we say that when we deal with as x closer to zero, okay, so this means, remember, if you have positive like this, it means it's getting close, getting closer to zero from the right side, or from the positive side, from the right. Okay, so it goes to it's approaching zero. Zero is here, right? So it goes through here from the right. So it goes to zero. And then when it's reached near zero, look at how it goes. Look my dot, the green dot. It goes higher and higher. And if you imagine 1 over, let's say, 0.000001, it is 1, 1, 2, 3, 4, 5. Well, perhaps that is our number, okay? Perhaps that's our number, a big number, right? So imagine that if we take the decimals and take the zeros as much as we can, then we will have a function that is getting higher and higher, and we could say it's getting an infinite numbers, right? Okay, so I hope you get the idea. And also same thing for the negative part is also getting lower and lower, so it's getting negatively large for the infinite number, right? So we could also say that in this vertical line, we could also draw a line that we call this is an invisible line, and we call this is the concept of the asymptote. Okay, so we have the vertical asymptote, and you have the horizontal asymptote, and both are at x equals 0 and y equals 0. Sorry, this is supposed to be y equals 0. Sorry, and this is as x equals 0. Okay, and perhaps this is also a review on your calculus 1 if you are taking my class right now. We have done this in the limit concept, and it's pretty much better. I mean not better, more details than this basic math. This basic math just goes through some concept that is perhaps we are not going to use that um, like we are going to use that just for proving some basic concept in mathematics, okay? But to make it more details, you need to go through your calculus, okay? But anyway, let's get through it for this course for a while, and let's see what we can try to make out from this basic of math, okay? Okay, now let me just give you some notes on the asymptote. So this is some notes, okay? So every time we are having some y equal to or getting close or getting higher and higher or getting lower and lower, when it's get approached to some numbers of x, that when we get the vertical asymptote. But the uh, when we increase x as much as we can, and then we see that the behavior of the functions is also getting approached to some constant, some number. Let's say in our case this is b. Then this y equal b is our horizontal asymptote. Okay, I think this is clear, and if we take this into the limit concept, it's become much more detailed, right? Okay, okay, but we can already say that we have an asymptote concept. Okay, okay, now the next part. So this is an introduction on rational functions. Okay, perhaps we have this 2 over x minus 3. Okay, now we have our default functions for our rational. Let's say our default functions is our 1 over x, like that. Okay. Now we could write this Rx. We try to factor 2. Let's see what will we get. Okay, we have this, and this is actually a function of x minus 3 of our f of x, right? Okay. So these two, remember the transformation of functions. This is stretched vertically. by factor 2, and then shift shift shifted 3 units to the right. Okay, and of course from this x minus 3 we could also conclude that there is a vertical asymptote when x equals 3. This is pretty much the same concept as this one. Okay, this vertical asymptote. Okay, because when x equals 3, the denominator will be equal to 0, which will be undefined on the functions, and we see that when 1 divided by, let's say, 0, it goes, or nearby 0, it goes through a higher number, and we say that it's going to have an invisible line, the vertical asymptote. Okay, and for this part we could also draw this. Okay, this is simply just saying the picture. Okay, the picture of the 2 over x minus 3. Okay, so this is what we call the transformation of y equal 1 over x. Nothing new. We have learned before previously in this previous sections about these transformations. We just applied again, but now in a rational functions. Okay. Now let's try another example. Okay, another example. Let's say we have f of x. Functions s is 3x plus 5 divided by x plus 2. Okay. Now, can we imagine how this as x transform from f of x 1 over x? Okay, so in the rational function, our base or our default will be this 1 over x. So this is also explain why these rational functions in chapter 3. Okay. In chapter 3, we learn some techniques related to the rational functions. Okay. We have the polynomial long division, and we have the syntactic division. Okay. Now I think we could just do the long divisions just to rewrite the form, and this is one useful method, and this is actually still applicable when you learn calculus. Okay, so let's solve this. Let's try to make new new equation from this. So this is 3x plus 6, and it's negative 1. So we could write that s of x, we could write this is 3 minus 1 over x plus 3. Okay, this is the same thing. We just rewrite it. And what's the deal for this equations? The deal is we can separate this big chunk rational functions becomes two more simplified functions, right? And we could imagine we could take some process that we say that, let's say, let me write 1 over x plus 2 in the front, that we could say that this is actually how it looks like. Okay. So we are having functions of f functions. Okay, this one. We could shift to the left 2 units and then mirror. Okay, so we shifting 2 units to the left, and then mirroring or reflecting through x-axis and shifting 3 units upwards from here. Okay, so we define this f first, and then we plus, and then so we transform the first one, and then we shifted the +3 at the end. Okay, I don't think I need to graph this. Okay, but I hope you get my point. Okay, we will see that because it has x plus 2 in the denominator, so you could predict that the asymptote will be x equal -2 for vertical asymptote. Okay. And we also see that from this Sx, when this is going to nearby 0, s of x is still 3. So perhaps y equal 3 will be horizontal asymptote. Okay, we could also take some conclusion from that. All right. What else that is important? I think for asymptote, um, we could just focus on the let me give you an example. Okay, for now, let the Rx okay. Now, if we look on this quadratic equations on both denominator and numerator, perhaps we could start from denominator to see whether we can factor these equations. Okay, let's see. Okay, to factor, we could try my method here. So 2x, x, and then this will be maybe this will be 1 or 2. This is -1, and that's true, right? So 2x minus 1 and x plus 2. So we have, for now, that x equal half and x equal -2. Both of this, I will write here, this will be our vertical asymptote. Okay. Now to find the horizontal asymptote, let me write to find horizontal asymptote. We need to make sure first the degree of numerator and denominator are the same, and leading coefficient over leading sorry, should be numerator and same denominator. So we are going to look on the coefficient. So we have 3, or here, sorry. So 3 and 2. So this will be equal to 3 over 2. So we could get that the y equal 3 over 2 will be horizontal asymptote. This is the theorem for the horizontal one. Okay. Actually, we could see from the text. Let me just copy. Okay, this is the how to find the asymptote for now for basic math. How to prove this is actually we need to have a concept of limit. Okay, but we are not talking limit in basic math. So yeah, we just have this to find the asymptote. Okay. Okay, I think there are several parts that um, I think we are going to skip that for a while. But the last thing on the rational that is important is the slant asymptote. The slant asymptote. Okay. So if R of x is P over Q like this, okay, both P, Q is polynomials, we could rewrite as okay, like that. So of course this is supposed to be the degree it's not P, sorry, it should be R because it's from the remainder. So the degree of R is less than Q and A is not equal to 0. Now this AX plus B, okay, this is what we call a slant asymptote, or sometimes we call it an oblique asymptote. So usually it comes out as a linear function or linear equations that perhaps this is not horizontal, not vertical, but it's a line equations. But it works like an asymptote. Okay, it works like an asymptote. Well, we could see some example. Let me just getting through quickly here. Okay, if we take this to find on how to sketch this graph, okay, let's say we are going to factor out. We get the intercept. For x-intercept is 1 and -1 and 5, right? And y-intercept is 5 over 3, right? 5 over 3. Because when we put x0, it's perfectly 5 over 3. And x equal 3 is vertical asymptote, right? And there is no horizontal asymptote because we have 2 and we have 1 here. So there is no horizontal asymptote. We could write no horizontal asymptote. And then we could try to find because this this is less than this, then perhaps we could try to have, um, well, logically speaking, if we have a quadratic and we have linear, when we divide this in a long division, there will be something left that is linear, right? Because we should have at least x, okay? And that's true when we deal with the long divisions. Well, let's divide. So take x, -4 plus 3 is negative x, -5. So this will be plus 1, right? Plus or minus 1, supposed to be, because it's going to be negative x, and plus 3. So we will have -8. Okay, and then we stop here. So we could write the Rx as x minus 1 minus 8 over x minus 3. And we could say that this x minus 1 is our slant asymptote. Okay, well, the picture, let me draw. Okay, this is the picture. Okay, just some additional picture. So we see that the slant asymptote, this is the y equal x minus 1. It is slant asymptote. Okay, that's it for the additional information. Okay, so now we are going to move to the last sections in the chapter 3. This will be the inequality. So this will be the polynomial. Inequality. Okay. So I think I will just give you examples and we can just move on from that examples. Okay. So let me give you example. 2x cubed plus x squared plus 6 is greater or equal 13x. Okay, to solve this is actually the same thing with the previous polynomials that we have. So we need to factor out, and we need to use same techniques like synthetic divisions or the card rule. Okay, we can also use that as well. So first is we rewrite this form. Okay, and then we need to try to factor this out, factor or use a synthetic division. So perhaps to make it simplified, we can think this in terms of finding zeros as usual. So we are going to take factor 6 over factor 2 as our possible ratios or possible zeros. So we will have okay, and we know that from the Descartes rule, this is 1, this is 2, so 2 positive zeros or 0 positive zeros. And we now have 1 negative 0. So you could check using the same principles like before. We could take the synthetic divisions. Okay, that's this. Maybe 2. We could check 2. Okay, I think we could. Let's try to factor out this. Can we factor this out? I think this is the factors, so we could factor. Okay, this is our factors. So we could take this and make it the factors into our inequality. Okay. Now to finish off the sets, we need to make our line numbers as usual for inequality. So every inequality, we should concentrate on making line numbers. Okay. Okay. And then trying some numbers from all possible intervals. Okay. So negative, negative, negative. So it should be negative. And then between this, we could take 0. So 0 is negative, negative, positive. So it should be positive. Okay. And then maybe taking 1. So this will be negative, positive, positive. So it should be negative. And taking positive, 3, positive, positive. Okay. Now based on the questions or the information we have, the factors or this whole equation should be greater or equal 0. Okay. So we need to include all the numbers that is actually our zeros. So we are going to have the solution. Okay, that's the solutions. Okay, the same principle in inequality. You need to take line numbers, make sure to confirm all the sets of intervals, and then write down the solutions. Okay, and how the techniques should be, like how to factor out. We are using the polynomials technique, which is the polynomials synthetic division. Okay, and then we can also try to find the possible zeros, and then maybe predict how many positive zeros and negative zeros the polynomial will have. Okay? And that is how we get the to narrow our solutions. Okay, let me go through another example. Okay, another example is if we have rational. Okay. Okay, now to solve this, do not multiply this denominator with this. Okay, do not multiply. Okay, that is wrong way, wrong call, because we are not sure on how the domain will work. Okay, we have a set of interval that will be undefined in this rational, right? So the best way to solve this is to move 1 to the left side and simplify it. Okay, should take this 1 minus 2x. Let me just write this. So this will be cancelled. So we have 4 minus x squared divided by x squared minus 2x minus 3 greater or equal 0. Okay. Okay, and then we are going to factor. I think both of these equations can be factored out. So this will be the factors, and for the denominator we are going to have, I think this, right? Okay, now we know that the possible zeros are this part, right? The one that makes this equation equal to 0. And the one that need to be an exception is denominator, right? Because we can have undefined part on this denominator, right? When x equal 3 or when x equal -1. So when we deal with the line numbers, and when we need to confirm this, we could take, okay, the x -2, x2, x3, x -1. So we have to write all this possible. Well, we could say this is like a critical points. Okay, critical points. Okay, and then we check the positive, or the how the critical points will make out from this equation. Okay. So this will be positive, negative, okay. It's negative, negative, so it should be negative. Okay. And how about this between here? Maybe we could take -3/2. So it's positive. Okay. Still positive. And then this is negative and negative. So it should be positive. And we could take 0 for the next interval. So 0 is positive, positive, negative, positive. So it's negative. And then we could take from 2 to 3, we could take 5/2. Okay, 5/2. It's negative, positive, negative, positive. So it should be negative over negative. It's positive. And then we could try 4. Okay, it's also negative. So negative, positive, negative, positive, negative. So based on what we have, we should take this into our solutions. Okay. So we could write the solution is, okay, this. How we get this, I forgot to mention that this denominator We need to be. I think we could write that since -2 and 2 is closed interval, we could write with a closed circle, and for -1 is open circle, and 2 is closed, and this is open. So we could write like that. Okay, I hope you understand this. Okay? I hope you understand why the solutions like this and how to determine the open interval and the closed interval. Okay? Okay, I think I can give you some notes here. This is because when x equal -1 and x equal 3, it will be undefined. Okay. So I think that is essential parts on the inequality for polynomials. Okay. So the first thing is just a normal inequality like this one. We just take some times to check, and then perhaps we are using the synthetic division or techniques from the previous sections. And when we have rational, we need to move all subject into one side and simplify to rewrite the equations, and then finding the critical points, which is usually the zeros and the x that made the equations undefined. Okay? The exception numbers that need to be written down on the interval, and that will be the solution. That will be the solution. Okay. Okay, I think we could have more example on this, but I think that will be on maybe next week. So next week, as usual, we are going to have a review on a class. So I will take some review and then also giving another sections after this part. Okay, so this will be the end of chapter 3, the polynomials. Okay. Okay, the next part, this will be, I think, the end sections on today's course. This will be just an intro for exponential function. Okay, so first we give you the definitions. Okay, definition. So the definition will be exponential function with base a is defined for all numbers x, and we could write f of x equal a with power of x, where a is a positive number and a should not be equal to 1. Okay. Okay. So we could write f of x as 2 with power of x. We could say this is also exponential. G of x is 5 power of x, and so on and so forth. Okay. And some property that looks interesting for this introduction is let me give you the okay, this part. Okay, if you look here, so first, let's just take sometimes plug in some numbers to the exponential, and then we have another function which is the reciprocal of the base. So if the base is 3, we take 1/3, and then also take sometimes to check all the possible values. Okay, you'll see that the value will be having all reciprocal each other. Okay? And then when we take the values to graph our functions, we could have this. Okay? So this could have, or we could also say from here that this is this is 3 power x, and this is 3 with power of negative x. We could rewrite this into this form, right? And we could also think this negative is because we mirror through y-axis. So we could also think using the transformation of functions. So this is transformation, also transformation. Okay, so one of the property in the exponential is when we have the base is reciprocal of the base is reciprocal, so we could have the mirror, okay, the mirror through y-axis. And then we could take the graphs of exponential function. And one of the property also is the horizontal asymptote. Okay. So the y equals 0, it's become the horizontal asymptote. Okay. So when it goes through here for the a power x, for a positive, this is going to reach y equals 0. Not reach y equals 0, but it's going to close by y equals 0. And when we move x to the positive sides, and a is from 0 to 1, it's again reciprocal of the a, you could say that. We could see that it's going to reach the same y equals 0. So y equals 0 is kind of well, we could say it's like one of the attribute on this exponential function, and we could confirm and later discuss on how this relate to another sections which we are going to have. It's about the logarithm, and they are really having the same same property, the same behavior. Okay, and then we could also see, let me check again. Yeah, and the most notable numbers in exponential is what we call the Euler number, or E. And this is the illustration how to get to the E. One of the example is we have this this equation here, which we have 1 plus 1 over n with power of n. This could be best illustrated by the compound and interest. Okay, compound interest. Okay, and then we are going to see that we have the values is around this number. Okay, when we deal with the large value of n. Okay. So we could, let me check. We could rewrite this n, and 1 plus 1 over n with power of n. We could illustrate also with the this value. So remember the value that when we have this large n is going to be 2.718 something. Okay, and this number is actually same thing with, we call E here. When we deal with this E, it will be equal to when we deal with the log, it will be equal to 1. Okay, so there is something between 2 and 3 that is going to be equal to 1. This will be an introduction for the logarithmic so we could describe E in more even details. Okay, so this will be on the next, I think next week sessions. So I will end up until here the exponential, just some introductions, and we need to keep on going for the rest of the courses, and perhaps we are going to have another quiz, okay, another quiz, but maybe that after we have review. Okay, and we don't have any midterm. Okay, remember we are not having any midterm, so we are just focusing on quiz, focusing on homework, focusing on maybe later projects or group discussion. Maybe that will be on this December classes. The December classes will be more on discussion. Okay, so we still have exponential, logarithmic, trigonometric as a whole thing, and then after that we have the polar curve, vectors, system of linear equation, conic sections, and sequence. Okay, sequence. Yeah, I think that will be the rest of the classes, and yeah, in some parts I may skip some process and focusing more on practical approach. Okay, so this will be the end of our lecture. So see you next week for review, especially chapter 3, and after that review we will have another quiz, and then continuing the exponential and logarithmic. I think just very short, very quick. What the important thing, what the necessary property that we need to have, especially related to calculus. Okay, and then we move on to trigonometric. Okay, so that's all for today. Okay.